Hi, welcome to the second lecture on unsteady heat transfer. In the previous lecture we looked at heat conduction into a plate heated from one side. We only investigated the short times, meaning that heat was penetrating into the plate over short distances. In other words, a large part of the plate maintained its original temperature. What if you want to bake a pie? How long does the pie need to be in the oven? What if you want to cool a glass object coming straight out of the production line? Glass is made at a temperature of about 1500 degrees. How long does it take before the inner part is at 50 degrees? In the previous lecture we discussed penetration theory. This described heat penetrating from one side into a thick plate. We saw that a smooth temperature profile progressed over time further and further into the plate. The penetration depth played an important role. It tells us how far the heat has roughly moved into the plate. Moreover, it gave us a simple yet exact way to compute how much heat is flowing in through the side of the plate for any time t. However, the penetration theory does not hold for the entire heating up of the plate. It is needed that the right-hand side of the plate is still at the original temperature T0. We could express that in a simple rule. The penetration depth must be less than half of the plate thickness. In many practical cases, the plate will be placed in a hot or cold environment and it will be heated up from both sides. Thus, we will concentrate on this case. It is depicted in the slide. Now heat is coming in from both sides. We already dealt with the start of the heat process via penetration theory. At some point in the middle of the plate is also heated up. This is for instance the case when we look at the black line. The temperature profile looks much like a cosine. And indeed, if we would mathematically compute the temperature profile, we would see that it is cosine-like. If time progresses, the temperature rises everywhere. But as we see from the blue, the grey and finally the white line, it stays like a cosine. Only at every instant with a smaller amplitude. Finally, the amplitude is so small that we could say that the temperature of the entire plate is T1. Now that the driving force is no longer T1 minus T0, we need to decide what is our driving force. One obvious choice could be T1 minus T center. That is a good choice. But in practice, also T1 minus the average temperature of the plate is used. That is especially handy when we need to find the change of the mean temperature itself. We model the heat flux in the usual way. Phi sub q double dash is h times the driving force. Once we know h, we can compute fluxes. As always, we prefer to give Nusselt instead of h, as it's more universal. We find h by multiplying Nusselt by lambda and dividing it by d. Note that lambda is the conduction coefficient of the material, not of the surrounding gas or liquid. Moreover, d is the thickness of the plate. We obviously have two different values for Nusselt depending on which of the two driving forces we have chosen. Nusselt sub c corresponds to choosing T center in the driving force. It is a constant and does not depend on time, as was the case in penetration theory. When we base the driving force on the average plate temperature, we also have a constant Nusselt number. In this case, it has a value of 4.93. When can we apply this theory? When we look at the slope of the temperature profiles, we see that both are quite far into the plate. More importantly, the original temperature T0 is no longer present in the plate. This happened at what is called long times. We thought that then both h and Nusselts were constant. This is true whenever the Fourier number AT over d squared is larger than 0.1. Compare this to the short times. Now heat is moving in from both sides, thus the penetration theory is valid if penetration depth hasn't reached halfway the center. Thus it must be smaller than half of half d, that is smaller than d over 4. If we turn this into a rule for the Fourier number, we see that when the plate is heated up from both sides, penetration theory is valid only for AT over d squared smaller than about 0.02. Thus there is a gap in our theory. Short times and long times are separated. Luckily, this problem has been solved completely. The solution for any t has been put into graphs. The graphs show various lines. First, we look at the two red lines. The full line gives the temperature of the center of the plate or strip as a function of time. The dashed line gives the mean temperature. The horizontal axis is time made dimensionless. It's actually the Fourier number, A times t divided by d squared. The vertical axis shows the mean or center temperature with respect to the wall temperature made dimensionless by the original temperature difference T1 minus T0. Note that the vertical axis uses a logarithmic scale. This graph gives the solution for all times, but obviously for short times the precision of reading the graph is rather poor. You better do the short time analysis with the penetration theory to get accurate answers. Note that there are two more lines drawn in the graph. They belong to heating up a sphere. This goes much faster than a strip of the same side, as is evident from the graph. This is logical, as the heat comes in from all directions. Moreover, when it moves inwards, it leads to heat up less and less material as the interior gets quickly pretty small. Again here, the mean temperature drops faster than the center temperature, which is also logical. The center is furthest away from the warm surroundings and thus has to wait longest before the heat flow has reached it. Let's go back to the long times. We have seen that for a plate, the heat transfer coefficient became a constant after long enough time. We could write this as Nusselt is 4.93. H becomes also a constant for objects of other shapes. Two of them are particularly relevant: the sphere and a long cylinder. Long meaning that its length is much larger than its diameter. That way we can safely ignore the heat flowing in via the top or via bottom. There is also an exact solution for this very long cylinder as there is for the sphere. We can sum them up. For the long cylinder, Nusselt is 5.8, and for the sphere, Nusselt is 6.6. Note that we have now two Nusselt numbers for conduction and a sphere. The first one we learned when Nusselt is 2 and dealt with steady-state conduction from a sphere surface into the surrounding. Now we add Nusselt is 6.6. That is for unsteady heat transfer inside the sphere. Keep these two apart in your memory. It is good to compare the short times to the long times. We can make a simple table with the most important characteristics. We are going to look at the heat flux and compare the driving force and the heat transfer coefficient for short and long times. For short times, we found that the driving temperature difference, T1 minus T0, is a constant. The heat transfer coefficient, however, was a function of time. For long times, this is just the other way around. Now, the driving force is a function of time, as T0 is no longer present in the object. Luckily, the heat transfer coefficient is now a constant. Let's do an example. Suppose you want to boil an egg and have it hard on the inside. Egg solidifies at a temperature of 65 degrees. Thus, the question is, how long should you boil an egg if its temperature everywhere needs to be at least 65 degrees? Clearly, this is an unsteady heat conduction question. Moreover, it is long times, as the original temperature in the egg, which is room temperature in our example, is no longer present in the egg. We are going to model this using the theory we developed. All we have so far is theory for a plate, a long cylinder and a sphere. An egg is closest to a sphere, so we use that. So in summary, we have conduction of heat in the egg. It is an unsteady process and it requires long times. Obviously, the last point to heat up in the egg is its center. Thus we can use the graph for T center. First we compute the dimensionless temperature of the center. That is Tc minus T1 divided by T0 minus T1. Putting in the numbers with T1 the temperature of the egg shell, that is 100 degrees of boiling water, we find the value of 0.44. Then we read in the graph the full blue line and find for the Fourier number 0.035. Next we estimate A, the heat diffusivity. For egg, that value is about 1.4 10 to the minus 7. We also have to estimate the size of the egg. It will be roughly 4 centimeters in diameter. From that we can compute the time needed, which is 7 minutes. Not bad at all. Ask your mother or try it yourself. Suppose you were really hungry. You didn't want to boil a chicken egg. Instead you took an egg of an ostrich. How long do you have to boil this egg? Well, the analysis is basically the same. You use the graph, compute the dimensionless center temperature, which is of course again 0.44, as we haven't changed any of the temperatures. From the line of the sphere, you find the dimensionless time, which is of course also the same, 0.035. The heat diffusivity is the same. All eggs are made of more or less the same material. Only the size is different. An ostrich egg is about 12 centimeters. Thus, now we find the cooking time 1 hour. Perhaps boiling a few chicken eggs at the same time is a quicker way to get sufficient food. Do you remember the analogy of mass transfer with heat for short times? Pretty much everything stayed the same. All we had to do is change A for D and delta T for delta C. Other than that, all ideas were the same. Well, guess what? For long times, that is also the case. The picture of the heat penetrating and the object getting warmer is just replaced by a completely similar one. But now with concentration and diffusion of mass. We write the mass flux as K times the driving force, for instance based on the mean concentration. Then we give Sherwood instead of K. For the shapes we studied, this gives for the plate, Sherwood is 4.93. For a very long cylinder, Sherwood is 5.8, and for a sphere, Sherwood is 6.6. Note, like before, that we have to be careful with the letter capital D. Italic for diffusion coefficient, plain for size. That's all for today's lectures. Do some of the exercises yourself and take a good look at the example of the glass plate. You have now followed 2 long lectures on unsteady heat conduction. This concludes all theory that we discuss in our transport phenomena MOOC. Next week we will take a look at all kinds of examples. No new theory will be added. See you next week.